All right, let's go ahead and get started. Good morning or afternoon for some of you who are not in the States. For those of you who don't know me, my name is Lori Penizak, and I'm a geologist here at Spectral Evolution. Thank you for attending today's webinar on porphyry copper deposits, where we are going to discuss these from the spectral perspective. So it looks like we have a good mix of both current users and new users of this technology registered for this webinar. So this is going to have something for everyone. So if you're an experienced user, make sure you stick around until the end so that you can see the advances in this technology and the increase in data quality that you'll get. And if you're a new user here, you'll get a brief summary and explanation of how to actually use a field spectrometer and utilize it for your porphyry copper deposits. So the outline for today's webinar will start with a very quick introduction to Spectral Evolution and the products that we offer. We'll then go into an overview of porphyry copper deposits and alteration types from the spectral perspective. And we'll actually take a look at some ultra high resolution data and also have a live EZID mineral identification software demo as well. All right, so real quick, I just want to introduce Spectral Evolution to anyone here who is not familiar with us. Spectral Evolution is the leading manufacturer of high-quality, full-range spectrometers and spectral radiometers. Now, we thrive on innovation, and we produce the best field spectrometers offered in the market. So we were established in 2004, and actually our 20-year anniversary is this Saturday. So this is a huge milestone for us. Our facilities are actually based out of the US, but we do have distributors worldwide. So we have product lines for a variety of different industries and applications. So for various hyperspectral applications, remote sensing, vegetation, mining and geology, obviously, and also photonics and calibration transfer. So if you are interested in any of the other applications that are listed here, we do have a webinar series every other month that covers these other applications as well. All right, so this is really for anyone who doesn't know anything about the technology and just needs a quick little introduction. So this technique of using shortwave infrared spectroscopy is a method that's been around for a really long time, and it allows us to identify bonds in minerals that have reflectance or wavelength features that have been characterized. And there are numerous libraries out there that can provide the service and understanding of the analysis of this data, similar to our EZID software that we'll see a little later on in the webinar. So we offer 3 different models for our mining oreX-series line of field spectrometers. And a lot of you here are currently using or have used a field spectrometer similar to the oreX-Express here on the left, where its spectral resolution is 2.8 nanometers, 8 nanometers, and 6. This is considered standard resolution. However, most people are upgrading and choosing to use higher resolution instruments nowadays. So this is where the oreXplorer and the oreXpert come into play here, where you actually get an upgrade in spectral resolution. With the oreXplorer, you're seeing the majority of the increase in resolution in SWIR 1 and SWIR 2. So you go from 8 and 6 nanometers to 5.5 and 5.8 nanometers. And the oreXpert here on the far right, this yellow one, this is actually the highest spectral resolution field portable spectrometer in the world. So you get a spectral resolution increase in all 3 regions, so the UV-Vis, SWIR 1, SWIR 2. If you compare this spectral resolution to, say, the oreXpress, you get double the spectral resolution. So you will see exactly what I'm talking about later on in the webinar, that when we use the oreX-series on very key important alteration minerals, this actually allows us to see more distinct and additional features that we would not see with standard spectral resolution. So these instruments are portable in the sense that you can use it in the lab, you can use it in the field. If you take it into the field, you can either put it into a backpack, or, a lot of people actually registered for this webinar right now, you are doing a lot of work in the core shack. So a lot of people like to actually just put their instruments on kind of like a rolling cart. If you're in the core shack setting and maybe you have access to a little portable generator, you can actually run these units on external batteries. Now, in terms of accessories, we have an entire list of different accessories that you can use with these units. The two most popular are definitely going to be our contact probes, which we have two styles of. The probe here on the left is a 10 millimeter spot size that has a sapphire window. And the probe on the right is going to be our mini probe that has a 3 millimeter spot size. A lot of people use both of these probes, but depending on what your application is, one might work better for certain, minerals or certain applications than the other. For example, if you're looking at the white mica alteration, you might want to use the larger spot size so that you can get a better average of alteration, whereas the mini probe is going to be really good if you're trying to focus in on a specific vein or a specific spot on your sample. But the basic sense here is that minerals like clays and phyllosilicates, for example, that are going to be present in different types of deposits, like porphyry copper, for example, these are going to have very specific elemental or wavelength signatures that are going to be related to specific mineral composition. And we can identify these using the field spectrometer. So, for example, muscovite. So a lot of you here are here to work on white mica alteration, right? So what you're going to do is you're actually going to focus in on the 2200 nanometer region. And so this can be used depending on, where that wavelength falls or how, wide that trough or feature in the analytical result from your analysis can be. So this can be used to determine the crystallinity and in some cases the composition of that sample, which is dependent upon those hydrothermal fluids from which that mineral crystallized in both composition, temperature, and pH. And so whenever you use a field spectrometer to take spectral measurements of these samples, you can plot out that data like we have here. This is actually a really good figure from GMAX in 2008. And so this gives you a good idea of, where you're at in your system. So before I go more into actually alterations in these specific types of deposits, I just kind of want to, tell, new users that, there are many, many tools and focuses that we use exploration geologists for porphyry copper deposits in general. But it's identifying these key features and these mineral assemblages that leads to discovery of these large scale systems. And why that's important is because porphyry copper deposits are found throughout the world. So being able to have access to a technology that allows for rapid, non-destructive mineral analysis is a huge benefit. So this is where using one of our spectrometers from our oreX-series line does come in handy. So let's finally discuss the application of these porphyry copper deposits and the spectral data that you will be seeing using this type of technology. So again, the key feature here is going to be identifying these alteration assemblages. So what we are looking for is that what's distal and what is proximal, and how can we identify, those as geologists in the field, as well as improving that in the lab or in the core shack. Well, the answer to that is you can use a field spectrometer to identify these important assemblages, as in the propylitic zone, where you'll see more of, the chlorite epidote assemblage. Sericitic zone, you'll see more white mica alteration, and potassic, which you can, have both biotite and potassic feldspar rich. So this is a model here created by Dr. Robert Lee at MDRU, illustrating how we understand the various assemblages or mineral assemblages that often occur in these porphyry copper systems, which are related to the minerals that are present within those systems. And if you kind of think about the formation of these key components, they often form under specific conditions, which we can then use to determine at, what temperature, depth, composition, acidity of the source. That again gives you an idea of maybe how far away potentially you are from the source of the fluids. So this diagram here on the right is actually from the CIM Porphyry volume that MDRU published in 2021. They do fantastic research there at MDRU. So this is showing that at higher temperatures, high acidic positions, you usually get the formation of potassic alteration of potassium feldspar, biotites, anhydrites, topaz at depth. And then at conditions of vertical ascent, you will get a fluid buffered component and generally form your more intermediate to advanced argillic alteration with clays of porphyry, dickite, kaolinite, among other things, which is actually where that ultra high resolution oreX-series will come into play. So we'll take a look at some of that data a little later on. But if you were to travel laterally in the fluid system, away from that larisite, you tend to get more rock buffered or meteoric fluid components. So you generally get more near neutral compositions of mineral components such as epidote, chlorite, illite, smectites, and these can generally be found away from the deposit. So all of these alteration types can be identified with a field spectrometer. And because it's so fast and easy to use, this is a very popular type of tool to use for this kind of deposit. So here is a porphyry copper model. This is by Scott Haley that really shows how all of this comes into play from a spectral perspective and how to better understand how you're tracking these spectral shifts and changes as you move throughout these various alteration zones. So you can see that you can actually track the white mica's ALOH wavelength shift at 2200 nanometers, and it can actually be used to map gradients in hydrothermal fluid composition, pH, and temperature. Here is another example of how this spectral data is utilized. So this is a figure from Zeng and others showing the mixtures of white mica and chlorites, which you would absolutely encounter in these deposits. So you can see that as you move top to bottom, how the feature at 2200 to 2500 nanometers region changes as you go from seeing just white mica to chlorite to a mixture of both. And so in this region here, you're going to see how that changes. All right, so let's take a peek at what these various mineral assemblages look like for each type of alteration within these deposits. So this is all going to be showing standard resolution data. All right, so one of the discoveries that's really been made in the last few years with new mapping and new identification of minerals is the presence of sodic or calcium-rich bearing minerals at the expense of potassium and iron, which is an assemblage primarily of albite, actinolite, with some epidote and chlorite, plus or minus potentially titanite or garnet. And this alteration typically occurs at or below depth, where you can have a connate or brine of water that's been pulled in. But you can see in the spectral plot here on the right, we have distinct spectral features and wavelength positions of these minerals. So if you're measuring core and you start noticing, this mineral assemblage, it will give you a good indicator that you are either below the system, or actually could be that you're just missing the upper part of the package and you're just directly adjacent to something that's more mineralized. In this case of potassic alteration, this is where you get the addition of potassium and iron at the expense of calcium. And often, this can be observed with feldspar veining, biotite veining, with plus or minus magnetite or anhydrite. But you can also get epidote in these systems as well. So, you can use the spectral data taken with these field spectrometers not only to identify this type of assemblage. Now, I should note really quickly that feldspars are not SWIR active. So in this case of feldspars, you would need to utilize another complementary method, which most people do for that. However, you can use the epidite chlorite mineral scaler with this specific spectral data to determine the composition of that epidote in the potassic setting, because it is much different than, say, in a sodic or propylitic setting. So let's get into the propylitic alteration. So this is where you get more of the oxygen or carbonates and sulfur and water in these settings, where you're going to get more of a hydrous mineral assemblage. This is often dominated by epidote, depending on the temperature and the depth of these fluids as they extend outwards. And the amount of carbonate or oxidation state of these fluids as you move outward can really provide you, the opportunities of seeing hematite dusting or even a hematitic reddish zoning around these propylitic halos. So being able to identify these mineral assemblages with a field spectrometer like you see in the plot here, this can be used as an indicator of direction or orientation of that halo. Now, the sericitic or philic alteration is the primary addition. So it's a hydrolytic alteration assemblage where you're going to get the formation of muscovite if it's very fine-grained, often referred to as sericite, plus the main ore-bearing mineralization. But these are generally confined to the few hundred meters or even up to a kilometer around that main source of the ore body. So here, tracking the mineral assemblage like you see in the plot to identify that sericite change is going to be crucial. And, again, we do that by keeping an eye on that spectral shift from muscovite to sericite to illite at that 2200 nanometer feature. And lastly, just to quickly kind of go over the intermediate and advanced argillic alteration, keep in mind that when you identify these alteration assemblages, like you see in the plots on the right, they are widespread overprinting on these other types of alterations. So you need to be able to have a good understanding of where you're at in your deposit at this point. Here we can spectrally track the kaolinite and the dicite occurrences with the 2170 nanometers to 2200 nanometer feature, which will actually allow us to see, where we are in the intermediate argillic zone. Whereas in that advanced argillic zone, we have very important alunite compositional changes that we can track. So in the spectral data from 1480 to 1495 nanometer regions, we can actually identify whether that alunite is maybe a more potassic or a sodic variety, as well as the important pyrophyllite features to help determine that, we are in fact in a high temperature setting, which indicates an advanced argillic alteration. So just to kind of wrap up this section in particular, you can see that these important alteration assemblages, and crucial alteration halos of these porphyry copper deposits contain distinct spectral absorption features that can be mapped using hyperspectral remote sensing data from a field spectrometer like our oreX-series line. So you can track these compositional changes of important minerals like alunite, kaolinite, porphyry, which have specific wavelength positions. And crucially important is going to be able to track that 2200 nanometer feature of the sericite, again, which is a good indicator that you're close to the main source of that ore body. And finally, being able to track, the temperature and the compositional changes of that epidote chlorite is also super handy by using a field spectrometer. So again, these instruments, they only take about 3 seconds to take a measurement in the field, and they require no sample prep. So you can get through a lot of core and a lot of rock samples throughout the day, which is, inadvertently going to save you a lot of time and money in the long run compared to, maybe sending these samples out for chemical assay. It's a quick tool to give you that much needed information right then and there, and is oftentimes used complementary with other techniques and methods. So, if you're not currently using this technology for, your field campaigns or your drill campaigns on porphyry copper deposits, I highly recommend you do, because this has been a tried and true technology for a long time. All right, so let's get into looking at some ultra high resolution data actually taken with the oreXpert. So I will be doing a live EasyID demo at the end with some ultra high resolution data that we can actually zoom in and see some extra features that we wouldn't normally be able to see with the standard resolution data. I should note that some of the minerals within these deposits don't necessarily benefit from ultra high resolution on their own, but in the cases of mixtures with minerals, for example, like a lot of clays and these phyllosilicates, the increase in this spectral resolution is, which you're really going to be able to help out with these vectoring, campaigns. So let's take a look at some actually data that's actually from a porphyry copper moly deposit. All of these samples that I'm going to be showing throughout these next few slides came from MDRU. Again, they do fantastic work on porphyry copper up there in BC. So all of this data was taken with MDRU's oreXpert. So up first is going to be this potassically altered megacrystic granodiorite. And so this screenshot that you see here is actually from our EasyID mineral software, where you have the red spectrum being the built-in library spectrum. The blue is the target sample that was measured. So this is being compared to our ultra high resolution mineral library called GeoSpec. And you can see the picture in the bottom right here. That was the sample that was actually measured. To the top of that is going to be our built-in mineral scalars. So you can actually identify the white mica by placing these green match regions in. So we placed a match region at 1400 nanometers and at 2200 nanometers. This is going to be regions E and D. And we were able to accurately identify the muscovite. So if you look down here at the bottom right, match regions E and D, we were able to identify that white mica. Most importantly here as well is we were able to identify the epidote. So in this case, we added a region at 480 and 1550 nanometers, which are, and also a feature down here at 2340 nanometers, which are regions A, B, and C. So you can see here at the bottom left, the match regions A, B, and C, we were accurately able to pull that epidote out of there. But we're also able to use mineral scalars for this. So we do have an epidote chlorite scalar here that is accurately identifying that 1545 to 1550 nanometer feature there for the epidote. And you have to remember that it is important to be able to identify this in these potassically altered samples, because The epidote here in a potassic setting is going to be much different than what you'd get in a sodic or a propylitic setting. So on to the next sample. This is going to be a cerussite chloride altered quartz monzonite. And the important features here that we want to highlight is being able to identify that white mica and the chloride. So we have the absence of the 1550 nanometer epidote feature, which is telling us that this is in fact chlorite rich, which we can see the chlorite spectral maturity scalar right here highlighted. We have a value of 1.61, indicating that low grade, with the presence of both MgOH at 2337 and FeOH at 2252 nanometers. So this is going to be related to that chloride itself. So if we look at this right region here, we are able to identify that clinofluor chloride there. But here we want to be able to identify the cerussite too. So because this is a chlorite-rich sample, we did need to unmix this spectra to find the cerussite. So we added a region at 1400 nanometers and also at 2200 nanometers, which does give us this cerussite match here in the bottom left. Lastly, we have this cerussitic altered quartz monzonite. And, this is really where the ultra high resolution is going to shine. This is where we're going to get to see some additional features in the kaolinite, which is going to be related to the temperature and the composition of this. So we can actually tell just by looking at the kaolinite crystallinity index scalar of this sample, we have a value of 0.923. So less than 1 is going to indicate a higher temperature kaolinite, which does make sense in this zone. So you can really track the temperature and the crystallization of these kaolinites with standard resolution as well. However, it is much more prominent with the ultra high resolution. So, with these additional features, especially here at the 1400 nanometer region, we actually now have a triplet there with an extra shoulder. Whereas data with a standard resolution instrument would only present the typical kaolinite doublet that we're all used to. So with that being said, let's actually jump over to a live demo of EZID so that I can show you all of these extra features in some of these important minerals within porphyry copper deposits and how we can use these extra features for vectoring purposes. All right. So here what you're going to be seeing, the red line is actually going to be a standard resolution data spectrum from the USGS mineral library, and the blue is going to be the ultra high resolution data. So the reason why I want to compare it to a standard resolution library is so that we can zoom in here and we can see this extra detail. So the first sample that I really want to show is prehnite. Whenever you're dealing with porphyry copper deposits, a lot of times when you're in the field, it is very difficult to identify prehnite in the field. So having access to a field spectrometer, whether you're actually on your field campaign or you're in a core shack, this is really important to be able to identify here. So I'm just going to zoom in here in this 13 to 1500 nanometer feature. Again, the red line is going to be the standard resolution. Blue is ultra high resolution. So in prehnite in particular, with standard resolution, you would get a singlet here at 1300 nanometers. You now have a doublet feature here with the ultra high resolution. Same thing with this 1425 to about 1475 nanometer feature. You now have an additional shoulder here at about about 1440, 1435. Let me zoom out here. And let's go over to more of that 1900 nanometers feature. So, you do have a lot more detail here in this 1900, well, really 1830 all the way to about 1910 feature. So you can see with the prehnite in particular, you do have a few regions of increased spectral resolution. So especially if you're on the hunt for that prehnite, ultra high resolution can really benefit you quite a bit. The next samples I really want to discuss is that kaolinite. So again, just to reiterate, red line is standard spectral resolution, blue is ultra high resolution. Now, in the case of kaolinite, again, we can use kaolinite as, more of that temperature-based crystallinity to figure out, are we in a high temperature setting? Maybe you're trying to see, okay, do I have presence of kaolinite, or is it kaolinite and a little bit of dicite as well? So if we look at the 1400 nanometer feature in particular, again, with standard resolution, we're all used to this typical kaolinite doublet here, but with ultra high resolution, this is now a triplet. So this in particular, again, can be used as a vectoring tool for temperature gradient here, as well as crystallization. If I zoom out, let's go down to the 2200 nanometer feature. You also have an increase in spectral resolution there as well. I mean, really throughout the full spectrum, you're getting an increase as well. So even if I go down here to like the 970 feature, you've got an increase in spectral resolution. So this can really help out, especially when you've got those mixtures. So the last one that I actually want to show you is going to be porphyry. So porphyry, can be used as a vectoring for that, again, those high temperature gradients. Typically, it's in those hydrothermal fluids. So there's a few different areas of interest throughout the spectrum that porphyry really benefits from ultra high resolution. So let me just kind of zoom in here. First area is going to be this 900 nanometer feature. Your 950 feature is a lot more sharp and defined, but you also have these small extra little features here. Zoom out and go into our 1400 nanometers OH region. You are really, let me zoom in a little bit more. You can really see here the extra resolution. So this is about 1405, 1415 nanometers. So this is 2 extra regions of interest. And if we zoom in more towards SWIR 2, again, you're getting much more detail in your ultra high resolution data. So with porphyry, kaolinite, prehnite, there are quite a handful of other minerals that do benefit from ultra high resolution. Whenever you are, whether you're using standard resolution or ultra high resolution, any of our spectrometers in the oreX-series line are really going to help out with this. So that is the end of the EZID demo. I'm going to go back to the webinar here. So my email is listed right here. So if you have any questions on the technology in general, how to, maybe add this type of technology to your fleet of technology for your, field campaigns or drill programs, and even if you're already a user of this type of technology, maybe you're interested in trying one of Spectral Evolution's products. If you're interested in ultra high resolution, reach out, send me an email. You can also find me on LinkedIn as well as Spectral Evolution in general on LinkedIn.